Hello, everybody, and I would first like to welcome you to the happy first day of fall, and welcome to our afternoon astronomy coffee hangout. My name is Tony Darnell of deepastronomy.com, and today I'm inviting you to take a break, grab a cup of coffee, and join us as we chat about some of the latest research from the field of astronomy. What we're doing here is in universities and research institutes across the world, an important part of being a professional astronomer is to stay abreast of the latest research being done by their colleagues around the world. And so almost everywhere, there are these weekly astro coffees that are designed to allow astronomers to an informal gathering place to just talk about the research being done by some of their colleagues in other fields. And so these hangouts are your window into that world, and we're inviting you to join us. These hangouts are endorsed by the American Astronomical Society and the American Astronautical Society, and we're highlighting the work and the research that's being done by these members of these organizations in these hangouts. Now, I want to point out that while these hangouts are endorsed by the AASs, any views or opinions expressed in them are not necessarily those of those organizations. So with that, I want to go ahead and get started, and I want to start by introducing my friend and colleague, Dr. Carol Christian of the Center for Emerging Media. Hi, Carol. She's the one that helped put these together. Very instrumental. Couldn't do it without her. How are you doing, Carol?
I'm doing well. And
okay.
All you folks? Okay, except it's not that happy that it's fall. I'm sorry. I'm a summertime person, so just saying.
I am, it's the same here. I always get a little sad when the nighttime gets longer than the daytime. I know that's counterintuitive, loving astronomy, but I'm the same way. I kind of miss the summertime as well.
Bye-bye, son.
Bye-bye. Anyway, happy fall, everybody. And today's the first day of it. Today, we're going to be talking about our solar system, and in particular, one of the moons of Jupiter, known as Io. And
talk about Io, bye-bye, sun. This is about bye-bye, sun, and what happens on
That's right, on the Jovian system. That's right. Good boy. Nice segue, Carol. That was good. Okay, so joining me, my guests today are Dr. Constantine Tsang. He's a research scientist at the Southwest Research Institute. Also joining me is Dr. Matt Richter. He's a researcher at the University of California and Davis in the physics department. He says he does astronomy in the physics department there. So welcome, guys. I want to thank you for joining us on our Hangouts. I want to set this up a little bit. So today, we're going to be talking about one of the moons of Jupiter called Io. It's a so-called Galilean satellite. And the reason they call it that is that when Galileo first pointed his rudimentary telescope up into one of the brightest dots in the sky, he saw something that looked like this. He saw the disk of Jupiter, which pull it up here. He saw the disk of Jupiter along with these little tiny, this is from his notebook, he saw these little tiny dots. And as he went, if you go down in his notebook, you can see at various observations, these little dots around the disk of the planet moved. And he correctly surmised that they are going around. Now, he's got most of these observations have only 3, but down here, you can also see there's actually 4. So there are 4 Galilean satellites, and they're called that because of the first observations of Galileo when he pointed his telescope towards it. Now, if you can do this yourself. If you want to go out and see with a pair of binoculars, you'll see something a little bit similar, but you might see a little bit better detail than what Galileo saw. Or you can also, if you have a small telescope, you might see something that looks like this. This is through an amateur telescope, and you can see the disk of Jupiter is very well defined. You can even see some detail in there, but you also see these dots on the side. Those are the Galilean satellites. And in particular, we're going to be talking about, I believe it's this one. I think that's Io. I can't tell from this image, but these are 3 of the 4 Galilean moons here. And finally, because it always has to show off, if the Hubble Space Telescope looks at Jupiter, you see this. You see something that looks like this. Now, you won't see this through your telescope, but you will see it. These are the images of Galileo. And what I love about this, Carol, and I know you're very familiar with this image, is that here you can see Io in the center here. Or there, I believe that's Io right there. You can see it casting a shadow on the planet itself. This is so cool. So this is Hubble showing off what it can see when it looks at Jupiter.
Actually,
okay. Oh, go ahead. Go ahead.
Actually,
Carol, I call on you.
Okay. Wait a minute. I lost my mouse. Help! Okay. Actually, in that picture, that's not the way the shadows are. The shadows are the other way.
Oh, did I do it wrong? Okay,
Yeah.
so let me just pull
Just
it back.
saying. Just saying.
Okay. Okay. So you're saying here that in this is not the shadow of that.
So notice that the object down on the right side, the object that's down to the left,
there,
that its shadow is very distinct.
Yes. So that would be there.
The next object, the big one, that shadow, because it's further away, is fuzzier, and it's that moon is more towards us.
Oh, I see what you're saying. So the further away the moons are, the more fuzzy the shadows are.
Now, in the leftmost picture, Io's shadow is very distinct because it's
would be
closer.
this one.
Yes.
Yes. Okay.
There you go. Sorry.
Good. Well, thank you for the clarification. No, I needed to get it right, so I'm glad you did. So so there's a little bit of an intro into some of the moons of Jupiter. We're particularly interested today in talking about Io because astronomers using the Gemini North Telescope in Hawaii, and we'll get into some of the things there, have found that when they observe this moon, there's a lot of strange stuff going on in Io. We're going to have our guests talk about it. The atmosphere seems to undergo these dramatic changes whenever the planet Jupiter comes in between the moon and the sun. So let me bring that up. So I'm going to start with my guest, Dr. Constantine Tsang. Welcome, by the way. Thank you for joining us. And so you've done some interesting work on Io. My first question to you is anybody calling it Io? Is it Io or Io?
I say Io, but I think some of my professors would say it's Io, but potatoes, potatoes. We know what we're talking about, right? Innermost moon of Jupiter.
That's what I'm just saying that because I remember back in the early 2000s, the Linux debate. And so I just wanted to talk about get that settled. Okay. All right. So I call it Io as well. So why don't you, first of all, just give us some background into the moon itself, and then we'll talk about some of your research. So talk about Io. What are some of its characteristics?
Sure. So Io is actually roughly the size of our moon, actually. It's something like 10% bigger than our moon, but it's basically on the order of the same size as our moon. And what's interesting about it is, in fact, if you look at the night sky, you'll see the size of our moon, right? X size. But if you are sitting on top of Jupiter's moon, Jupiter's clouds, looking up in the night sky at Io, actually the angular size, the size in the night sky of Io, compared to when you're on Jupiter, it's actually about the same size as our moon is from the Earth, because it's roughly the same distance and it's roughly the same size. And so you can imagine looking up at night, looking up at our moon, but imagine now that there's about 200 volcanoes on Io, and this really active world on Io is full of active plumes and volcanoes and lava flows that we've now detected on the order of something like 200. Wow. Which is an incredible place. So if you think about the size of our moon, but having a whole bunch of active volcanoes, that's the type of place that Io is.
So could we, and this is this environment presumably is due to its proximity to Jupiter, correct? And the interaction with it, is that right?
Right. So you have all the other moons, Callisto, Europa, Callisto, and Ganymede, and So what's happening, we think, is that as Io goes around Jupiter, it's being pulled by the gravitational force of Jupiter, being a large object by its orbit. But then on the outside of Io's orbit, you have Europa, Callisto, and Ganymede, and they're fairly large moons. They're big Galilean satellites. And so every time Jupiter pulls Io towards itself, all the Galilean satellites pull Io away from its orbit, and so you have this tug of war between Jupiter and all the other Galilean satellites. And ultimately what happens is that a lot of what we call tidal energy gets put into Io's mantle, and that heats up all the molten rock, and that's why you get the active volcanoes and lava flows that we see on the surface.
So Io is really in a sort of a victim of its location here. It's being pulled and tugged by all kinds of things that are in
exactly. And it's kind of like like a rubber ball. If you play squash or anything like that and you squeeze it, then you put a lot of energy in there and that starts to quickly warm up. And the same principle applies to Io's internal solid body.
Okay, well, what about the other moons? And let me ask you. Let me ask this to you, Matt. The other moons, and I should have spelled it out more correctly in my intro. We have Io, which is the closest, followed by Europa, which a lot of people are very interested in. Ganymede, which is the largest, I believe, of Jupiter's moons, and then following Callisto. Those are the 4 Galilean satellites. What are the other ones? Are the other ones being pulled like this, or is it mostly just Io that's under a lot of this stress? And I'll ask you that, Matt.
Well, Io's under the most stress, and I should preface this by saying if Con sees that I'm saying anything incorrect, he should jump in. This is
Carol will too. She's very good at that.
This is much more his research area, and I'm just going back to my solar system classes. But Europa also is getting pulled. It's the next moon out from Io, and the effect diminishes as you're getting further from Jupiter, and you're getting more of the mass concentrated on one side as well. But, you know, Europa is, we've recognized that it has an icy surface, and it seems to have probably a liquid ocean underneath that icy surface. Well, one thing that is keeping that water liquid is the fact that there's tidal energy on Europa. So that sound about right, Con?
Sounds about good.
And so I've got this. This is the Wikipedia page on some of these moons, and so I just wanted to. I hope this is coming out okay, but I wanted to show it because it gives a little view into some of the internal structure of what a lot of people believe these moons are like, and one of the reasons that people are interested in Europa is there's this believed to be this sort of well, I don't believe it's believed. I believe it's been confirmed. There's this liquid water underneath this crust here, this outer shell of ice. On Europa, and then of course Ganymede, being much larger, also has a variety of levels to it as well. But look at Io. I mean, Io is just one big. It looks to me like one big molten core. I don't know. What do you think, Con? Is that a good way to describe it?
It is. So we describe Europa and actually another moon around Saturn, which is Enceladus. We describe Europa and Enceladus as these ocean worlds. Where we think below the crust, below the surface, we have a liquid layer between maybe a couple of 100 meters to a couple of tens of kilometers. With Io, we think there's a molten ocean, effectively, that's being churned up because of all this convection that's going on and all this tidal heating that's going on within the mantle. So in many ways, it's also a liquid ocean, but instead of water, it's magma. It's liquid, silicon and magma. So yeah, it's quite an interesting dichotomy between Io and Europa for sure.
Right, and so here's the image you sent me of Io, and before I need to mention, guys, I didn't do this at the top of the Hangout, but this is a discussion and we want to involve you. We hope you will participate, and there are several ways you can do it. If you go to deepastronomy.com/live, I have a chat window open right there. You can interact with us there on the chat directly. I'm looking at it now. You can also use Twitter and use the hashtag AstroCoffee. I've got that up as well. So if you have questions or you have observations or things you want to know more about, please, at any time throughout the Hangout, we hope you'll join in and let us know what you think. So I wanted to point that out because I hadn't done that yet. Okay, so back to this image. So here's the image you had sent us of Io, and tell us a little bit about why is it this color? Mm-hmm. And it looks like when I first learned about Io, it was always described to me as a big pizza. And it does. Right. It looks like a pizza. But why? Why does it look this way?
So all the black. So first off, it's a lot of coloration there. It's pretty vibrant, pretty interesting. And in fact,
now, these real colors, by the way, if we go to Io, is that what we'll see?
Yep, this is pretty much, these are visible images taken from the Galileo spacecraft back in the late 90s, early 2000s. And what you see here, a lot of the black, I mentioned that we have active volcanoes spewing lava and sulfur dioxide. Well, all the black dots that you see on the image are volcanic centers. So these are
like this right here?
Lava flows. Yeah, so yeah, exactly. Those black, exactly. Those are active hotspots. If you look in real close-up details, you'll see right in the middle is like a volcanic center of lava, and all that black material is being spewed out from those volcanoes. And what you can also see is those ring structures you can see sometimes around those black black centers, they're outflow from the plumes. So when we think there's a lot of SO2, we know there's a lot of SO2 coming out, and you can see the plumes coming.
SO2 is what?
Oh, sorry. SO2 is sulfur dioxide.
Sulfur dioxide. Okay,
yeah,
that's important because we're going to get to that in a minute.
But yeah, these plumes, you have big eruptions just like on Earth. On Earth, you have things like carbon dioxide, which is CO2, and then you have water vapor, H2O, and then SO2, which is sulfur dioxide. And those three things are the primary constituents of terrestrial eruptions. On Io, we think most of it is pure SO2, sulfur dioxide. And what happens is that all that material then, forms a plume and then falls back down on the surface of Io, which is why you get those concentric circles. And then the color is like a proxy of what the composition of those things are. So you have all that red ring around, especially in the left image, you can see that huge red yeah, that's right, red ring. That's the Pele plume. Pele or Prometheus? One of the two, I get confused. But it's different sulfur mixes. So pure sulfur, which is just S, S2, S4, different chains of sulfur atoms that actually are colored differently. And so that's why you get a lot of the yellows and the oranges and the blacks. And then finally, you have a lot of the white stuff on the surface, and that's actually sulfur dioxide frost. This is ice that's condensed from the plumes, and that's actually white on the surface. So that's why
this is frost. Wow.
That's cool. Right. That's right. And so most of the coloration that you see there is because of the different compounds that's being erupted from the volcanoes.
Okay, so we've got this moon. It's in a place that is very, let's just say, problematic in terms of being able. It's always being pulled out by a lot of different forces, both from the big giant planet it's close to, as well as the moons on the other side, and it's causing all this tidal, this tidal friction and heating, and all this is constantly being pulled. Would Io have a lot of earthquakes, or is it just volcanic eruptions? Are there any I don't suppose earthquakes, I guess, presuppose plate tectonics, but right. Are there any ground, do you think, anything that happens in the crust that would cause earthquakes or ioquakes?
Yeah, that's a really good question. And I think the answer is probably not. We haven't seen any tectonic structures on Io. At least that's very distinctive that we see, on other places like, Venus and Mars. But most of the energy I think what's happening is because there's different theories of how the energy that you pump into Io gets out, and pretty much all of the theories revolve around these heat pipes. This idea that you have this molten core that's got a lot of heat and energy, and you transfer that heat towards space, the surface and the space, by having these huge pipes that vent lava through the crust. And so I think all the energy is erupted through active volcanism. It's probably almost no tectonic activity on Io, but we haven't landed on Io, so we don't really know.
Okay, well, let's talk a little bit about your research, and that brings us to this. So you guys have been observing this system, particularly Io, with the Gemini North Telescope. That's a telescope that is up in Hawaii. Let me just show up a quick image of that since you guys shared it with me. This is the observatory. This is on Mauna Kea in Hawaii, and it's one of a pair of telescopes. They have Gemini North and Gemini South. Gemini South is in Chile, and so this is the telescope you guys were using, ground-based, 8 meters, not a tiny telescope, so you get a lot of good images from it. And so you guys have been interested in looking at this moon. Now, because of all of the activity going on there, you've discovered, or maybe you didn't discover, but astronomers have learned that there is an atmosphere around this moon, correct? Why don't you tell us a little bit about the atmosphere and why, and what you think is causing it, sort of some of its properties.
Mm-hmm. Sure. Actually, the story actually goes back all the way back to Voyager days. So Voyager 1 and 2 flew by, most of a lot of the outer planets in the solar system back in 1979 and throughout the early 80s. And it was those missions that discovered Io had active volcanoes. And in fact, it was the first place discovered in our solar system that was geologically active. You think of, Enceladus, the moon of Saturn, having plumes of water vapor coming out. We think Europa has similar, plumes coming out of its surface. Well, Io was the very first, place in the solar system that we actually saw real geology, active, processes going on. And they discovered a total of about 7 or 8 different, active volcanoes, and some of those had plumes of gas, SO2, coming out of them. What we think is happening is that this SO2 coming out forms a global, layer, very thin layer of SO2 that's kind of bound by the moon's gravity. But then at some point, it gets cold, on the night side and behind Jupiter. So what we think is happening is at some point the atmosphere has to condense onto the surface, and you see from those images where the regions, in the white, that's all SO2, sulfur dioxide frost, that's condensed as an actual ice layer. And so the question became, does this ice then what we call sublimate? So you can imagine evaporation pretty easily. You're going from a solid to liquid, and then liquid to gas. Well, in the low pressures of space, you can get a process called sublimation, where you move from a solid to a gas instantaneously. But it's kind of like evaporation, if you want to think about it like that. So the question that we've been trying to ask for the last 20 years or 30 years of studying Io is, does this SO2 frost actually form the atmosphere as well? And so recently we've had some really interesting work thinking about that. And because one of the processes that, if this is true, if the ice does turn into an atmosphere, it has to be a strong response of the surface temperature. So you can imagine your sunlight is hitting the surface of Io and is evaporating all this ice off the surface. Or once it's orbiting around Jupiter, and so it orbits around Jupiter 1.7 Earth days, and in those 1.7 Earth days, 2 hours it spends behind Jupiter, in complete darkness. And so we think, well, if that's the case, then the atmosphere should actually what we call collapse. So if it's supported by all this, sublimation of the ice, then in shadow, in theory, we should see the atmosphere collapse. And so we tried to do this experiment recently, and it turned out that yes, indeed, this is actually what's really happening. So this graphic you see in front of you, to the left, we have this fully inflated atmosphere that is driven by this evaporation process, this sublimation process of the ice. And then as it goes behind Jupiter, we're able to follow Jupiter, go behind Jupiter.
You can see the shadow of Jupiter here in this illustration.
That's right. That's right. And it takes about, between, roughly about 4 to 5 minutes to go from complete, being sunlit to being in complete shadow, which is that graphic on the lower right. And so we can look at not just the temperature of Io, the surface temperature, and see how that cools, but we can also look at the atmosphere, the density of the atmosphere with the Gemini Telescope and with Matt's instrument.
Okay. Well, go ahead, Carol. Do you want to add something?
I just wanted to make sure that everybody sees and that I understand that in the image in the lower left, that's a spacecraft image of Io, and so the volcanoes, of course, still occur.
Yeah, so the lower left image is really interesting. This was taken by the Cassini spacecraft flying through the Jupiter system on its way to Saturn back in the year 2000. And this is Io, and the right side of it is all dark because it's actually coming out of shadow in this case. Yeah. Okay. And then on the left, you have the sunlit crescent. It's just coming into what they call daytime. And then the two bright spots on the right of the lobe there, at the like 3 o'clock position. Yeah, those two are big volcanoes that you can see emitting. This is kind of near the visible spectrum, just normal light. You can see how hot glow because it's the nighttime. You can see that. And
that's amazing.
It is. It's really cool. And then the blue and the orange that you see, kind of the glow, the halo around it. That's actually part of the extended atmosphere. These are the atomic species that you can see glowing in the light that this image was taken in. So there's a whole bunch of stuff going on that image on the left.
Well, I get what you're saying as far as the sublimating of the ice that's on the surface of the white spots that we had in that previous image. You see in this one here, I believe. Oops, nope. What am I? This one. I can see these white spots here being, sublimating into the atmosphere that you're talking about in, as it goes behind the planet. But what about these? And so are you saying that the atmosphere of Io is primarily that? What about the contribution of these volcanoes?
Yeah, so that's the whole question for the last 20 or 30 years. Is the atmosphere around Io solely driven by what's being pumped out of these volcanoes? Or is it driven by the ice? I mean, ultimately, the volcanoes bring up the sulfur dioxide from deep down within the interior, but that's the ultimate source. But what really controls that atmosphere? Is it there because you have all these volcanoes that's supporting it, pumping SO2, or does that just supply it to the surface as the ice layer, and the ice is what drives the atmosphere? And so this experiment demonstrates that it's really the ice that's driving a lot of the dynamics that we see on Io's atmosphere.
All right. Well, is that a segue for Matt to talk about the experiment? Well, I heard your instrument being mentioned, Matt. You want to describe that to us, please?
Sure. So I want to say that with Con and his colleague, Dr. John Spencer, we've been observing Io going back more than a decade now. And our instrument is a spectrograph that separates the light into its different components, different colors. So, a simple spectrograph you might think of is a prism.
Is it this? Am I got the right thing up?
Yeah, so you can see maybe the better one is, that's
that
more
one?
of a detailed view of our instrument, TEXES it's called, which stands for the Texas Echelon Cross Echelle Spectrograph. Really, the name doesn't add much to it, I'm afraid. It's John Lacey, who was my postdoctoral advisor at UT Austin in the astronomy department. This is an instrument that he came up with, and I was around helping him to build it, bring it to fruition. And we've been using it ever since we first went out to Hawaii in about the year 2000. It works at wavelengths much longer than visible light. So in what's called the mid-infrared, from about 8 microns to 25 microns. And just for reference, visible light is around 0.4 to 0.7 microns. So these are much fatter photons, as we sometimes call them.
I never heard that.
Oh, okay.
Fat ones.
So within this region of the electromagnetic spectrum, molecules have lots of spectral features. So it's not so much that we're looking at atoms and ions. There are some spectral features like that. We're really looking at molecules as the molecule is vibrating and rotating. The other thing is that the spectrograph has a grating. Its primary grating is almost 1 meter long. So, for me, I always do the graphic where it's put the finger in the center of my chest out to the fingertip. That's about 1 meter. You can see it in the left-hand panel of those two where you've got all the little lines going across it. Nope, on that drawing.
Okay.
And it's all the little lines that are sort of shading in. That is one chunk of aluminum that is 36 inches long and very precisely ruled, so it acts like a diffraction grating. The whole instrument is cooled down to liquid helium temperatures, so that's 4 degrees above absolute zero. And we need to do that because if it's too warm, the detector actually can't detect any light. It's busy just detecting photons from the material it's made out of. And
so this strip of aluminum, let me just make sure I got this. This strip of aluminum has got little tiny scores in it, very accurately placed.
Yep.
That split the light up.
Yep.
Wow.
And Because that grating is so big, or actually what I should say is because we wanted to study gas, molecular gas, and to do that we need to split the light up to 1 part in 100,000 of its wavelength. We needed a grating that long. And so when I was saying the molecules are important in the mid-infrared, or the spectral features, for this particular instrument, every design choice we made was to try and make it so we could study gas like Io's atmosphere, which is very low pressure, so the lines are very narrow. They don't, the light doesn't get split up in the spectral features very much. So if you go back to the picture of Gemini, yes, that one. So you can see there the telescope as a whole, an 8-meter telescope, and one of the perks of the work that we do is we get to go to these kind of neat places and have these really neat toys to play with. You can see the whole telescope on the left, and then in the red box zoomed in on the right, you can see Texie's instrument, which is the blue tube hanging down, right? And people over on the side for scale. It's about 6 feet tall, and it's essentially a giant thermos bottle that's housing that one really big grating.
Now, is this always on there, or is it just is it taken off and put on when needed?
So it's not a Gemini instrument. We actually, we are still the people who control the instrument. And we like to go to Gemini because it's such a big telescope. We can do certain projects there. But at the same time, there's a lot of other people who like to use Gemini. And so it's hard to get time. So we are generally on the Gemini telescope maybe 1 week out of a year. More frequently, we're at a neighboring telescope on Mauna Kea. NASA has a 3-meter telescope that's run by the University of Hawaii, the infrared telescope facility. And we are mounted to that telescope probably about 4 weeks a year.
Okay. So I guess the people that are charged with moving that around, they're probably pretty careful moving that thing around. It sounds to me like you want to be dropping that, do you?
You don't want to be dropping it at the same time. We use a pickup truck. We're just trying to be very careful and drive very slowly.
Okay, so these are some of the things we're looking at. What I guess I have I want to remind everybody you can chat with us at deepastronomy.com/live, and I'm seeing some of you have already joined, so that's great. And I'm going to get to your questions right after I ask this one. I know that you've shown us a picture from Cassini, a real picture, an actual picture, and then you've shown us a model with the illustrations of what you think is going on with the atmosphere of Io as it goes behind the planet, Jupiter, with the atmosphere. You even told us what you think causes this atmosphere. But but as we know, Juno is out there now. Juno has arrived, and I want to know, is there anything that you're hoping to learn from Juno about Io?
That's a good question. You know, it's somewhat sad. You have this amazing spacecraft that's around Jupiter, and it's going to do some incredible science studying Jupiter's atmosphere and its origins. But unfortunately, it won't be studying Io. Its prime focus is squarely on Jupiter for all the good reasons.
Right.
The other reason is it's also a spin space. It spins to maintain its orientation with Jupiter, and that makes it really tough to look at Io, which will pass through the scene, as it were, the camera's field of view very, very quickly. And so it makes there is one process that it is going to look at, which is related to Io, and that is the auroras. So Juno is orbiting around Jupiter pole to pole. And at the poles of Jupiter, there are auroral features, just kind of very similar to Earth's aurora. And what you do see is the footprints of the moons, the Galilean moons like Io and Callisto, on the aurora. So they're actually magnetic field lines that connect the poles of Jupiter to all the other Galilean satellites. And what happens is there's electrons that move up these magnetic fields and end up at the poles, creating footprints.
Wait a
And
minute.
so,
Whoa. So okay, hold on now. So you got the footprint. What do you mean? First of all, what do you mean by footprints? And it's going up. They're from the moons, and
right.
they're embedded in the aurorae that are on
That's
the
right.
poles?
So if you look at the aurora pictures, it's kind of like there's wispy, tendrils of light. That's the emissions from the aurora process. You can actually see small circular blobs moving around the aurora because those magnetic field lines are actually connected to the moons.
So those circular blobs, they're distortions in the magnetic field by the moons. Is that right? I mean, I don't get it. I mean, they're not the moons. They're not anywhere near the poles.
Right.
So,
But I mean, effectively, you're right. You've connected a chain, right? Imagine a link that goes from the pole of Jupiter, invisible link, to all these moons like Io, and as Jupiter and the aurora rotate, those links move with it. And so
you can see embedded in the magnetic field the distortions or the effect of the magnetic field of Jupiter that the moons have had.
Correct.
On it.
Correct.
That's amazing.
And we call those footprints because all the moons have this footprint, right? It's kind of like invisible lines that connect.
That's amazing.
That's one thing that Juno will be helping us study.
I learned a new thing today. That's awesome. I did not know that.
So for those of you watching, you should look it up. It's just go to Google auroral footprints on Jupiter, and you'll see it.
And they're the signature, the effect of the moon's magnetic fields. Well, is the effect of the moon on the magnetic field, which brings me to my next question. Does that mean these moons have magnetic fields of their own?
No, I don't think they do. It's because they're embedded, because Jupiter is quite a large planet, and its magnetic field stretches out, considerable distance, really far. And the moons are embedded in that magnetic field, so they interact with it. But by themselves, they don't really generate anything that's substantial.
I see. Okay, great. Okay, well, that's good to know. Okay, well, I got a really good question here from Larry Beckham on the chat. So he goes, he found the chat. Good. I'm glad. I hope it wasn't too hard. His question is, will all the forms of oxides from Io, could you harvest from orbit and separate the O2 for human use? So let's say we wanted to go there and we wanted to use some of these oxides and grab the oxygen. Is that possible?
I don't think so. I think there's easier ways of doing, producing energy without having to, take in what's around Io. Basically, I don't think. I mean, there is oxygen in the form of SO2, and then there's pure oxygen, just O, that's floating around Io, because those molecules break up in UV and produce, sulfur and oxygen separately. But I don't think anyone's thought about using them as anything else, for power generation or resources, because I think we have plenty of those to use around Io and Jupiter as well. So
yeah, in fact, if I were going to use Io for anything, I would use it to fight the Gorn. And if anybody knows anything about Star Trek, you know that you need lots of sulfur. So that's what I'd be using it for. So Matt, I have a question about these. Go ahead, Carol.
Yeah, I just wanted to say I'm sharing I finally found a Hubble image of the aurora and the dots so I'm sharing that.
Are there any footprints in there, Con?
Yeah.
Let's have a look. Sorry, let me have a look. I can't. I'll go to Carol's thing. Yeah. So those two those two, and then the really bright one on your 10 o'clock. That's it. That's the one.
Those are from the moons of Jupiter.
Yep.
Yeah.
Wow.
Yep. Yeah, so they're what we call the auroral footprints from the satellites. It's these you can imagine connected to those dots, magnetic field lines that drape out from from Jupiter and then impact the different moons because they're being perturbed within the magnetic field of Jupiter.
That's amazing.
Yeah.
Anyway.
Yeah, I just love that. Okay. So
all right,
Matt, I want to go back to you and your instrument with these molecules. You said you're very interested in the molecules, looking for those. You designed your spectrograph to look for them. So sulfur dioxide was one of the things. Do you have what other things were you hoping to find, or did you find using this instrument around Io?
So around Io, it's all been sulfur dioxide that we've been targeting.
Okay.
But in other places, like around young hot stars that are so young they're still kind covered by gas and dust. So you can't see them visibly, but they're heating up the dust and evaporating any ice that had been on the dust grains. You can study things like acetylene. You can find hydrogen cyanide. You can find ammonia, methane, and then also with Gemini as well, we started looking at some young stars about the same mass as our sun that have disks around them. The material that the stars formed out of, not all of it could come down into the star, and so some of it's in a disk going around the star. And we can actually even detect around some of those water vapor. And
wow.
What's tricky about that is, right, Earth's atmosphere has quite a bit of water vapor.
Yeah.
Has a lot of methane too. But there are certain, well, especially if you get to, well, it's kind of funny. You have to go to high energy water, hot water, and then you're better able to study the water around other objects because it's emitting light at wavelengths that aren't populated in our Earth, or that the molecule isn't in our Earth. Whereas for methane, you have to go to very cold methane to detect it easily. Well, that's not generally true. Where it was first detected in one of these systems, it was through its coldest transition. So
I like the high energy water thing. Carol, I want to rename these hangouts to the afternoon high energy water beverage hangout. No, hon, you don't think you're not laughing? Okay.
So anyway, that's actually closer to the type of work that I'm most interested in, is this study of what's going on around these young stars. Can we learn about what molecules went into the planets that form around stars other than our sun?
That's amazing. Well, that's great. Okay, well, that sounds like a great hangout topic too for another. Okay, well, I want to show this real quick, Con. This is a schematic that it came from your slides that you were talking about. This is the schematic of what you think is going on here. So as Io goes around Jupiter, there's this area, this is the orbit. As it gets close to the shadow of Jupiter, here's Jupiter's shadow. There's this light coming from the sun. This is sort of about the 2-hour window that you're talking about, right?
Yeah, so this is the top-down view, as it were,
Yeah.
and Io's, in this this orbit that is counterclockwise as you look at it from here, for instance, from the north, and then it then goes into this eclipse period for 2 hours, and we think the atmosphere basically literally collapses onto the surface as ice, and then when it comes out of eclipse, where Io, that red dot right now is Io comes out of the eclipse and back into sunlight, then the frost then evaporates off the surface and reforms the atmosphere. So the atmosphere continually collapses and reforms in the shadow of Jupiter.
Are these green squares the amount of time it takes to collapse and reform?
No, it's really an eyeball estimate of, they're the periods that we are looking for from the Earth. And, we can only do that perhaps, in this period of 1 month, in this 1 year period, where we can actually see Io go behind Jupiter.
Oh, that's a good point. You depend a lot on the orbital geometry of the solar system
so
to be
you can
able
imagine,
to make these observations.
Right. You can imagine, you have Earth, and then you're looking at Jupiter. Well, how do you look at Io behind Jupiter if Jupiter's in the way? Well, it turns out that, we're obviously in an orbit around the sun, and at the apex of our orbit, there's enough kind of an angle to look into the shadow. And that period, only comes up, once every 13 months or so. So this is it's difficult. Matt mentioned that, the instrument that we've been using, TechSegs, is on Gemini 1 week for the year. Well, now compound that with the fact that we have to be looking at Io at a very specific time within the year. So that's part of the trick with this experiment.
Wow. So this I want to talk about this briefly too. These are some of your results showing, for instance, from your paper.
Wiggly lines.
I'm sorry?
Wiggly
a bunch of
lines.
squiggly lines, but I do want to show.
Yeah, that's what a spectroscopist always gets to show.
That's-
None
I
of
know,
those pretty
strings of
pictures.
numbers. Well, we had to do it, right? So
They love this stuff.
yes. But to me, it looks like this is this the punchline here? Or?
Yeah, so let me just go back and say that, yeah, let's talk about the one on the right. So you have two panels on the right. The top one is actually just heat. We call it thermal flux, but effectively it's just heat radiating from Io itself. And the zero line is, you can imagine to the right of that zero line, Io is actually in eclipse, in the shadow behind Jupiter. To the left of it, it's in sunlight. So what we're doing... Yeah, go ahead. Yeah, so
I'm just following along.
Yeah, so what we're doing is you see there's dots at -40. Well, we're tracking Io 40 minutes before it goes behind Io for every 10 minutes. And then right at 0, Io starts to go behind Jupiter and goes into shadow. And the temperature falls off because it's not being heated by the sun anymore. So it starts to cool off. And we did that on 2 occasions. You can see both of these curves lined up really nicely. And the bottom panel is the exact same times, but now we're looking at the actual density of the atmosphere, looking at the absorption, the sulfur dioxide in the atmosphere, and at the same time as the atmosphere, the surface cools, the atmosphere density is dropping with that. And so this gave us basically the big clue that actually, when you remove sunlight, when you remove the heating effect on the ice, then the atmosphere starts to condense onto the surface as ice.
Okay, so and I want to mention these panels on the left here, but I don't want to go into too much detail other than to say these are the data, right, that you used to make. Well, maybe you should just describe what these are. I'm not sure. Just as brief,
Sure.
Using broad strokes, if you could.
Yeah, broad strokes. So the black lines, the wiggly black line is the data itself from the telescope. This is just what we call a spectrum. So if you split that light component into different components, you can see there's some deep absorption, what we call absorption features. That's those things there, right? And that's the sulfur dioxide absorbing light.
And it's doing it at this wavelength here.
And these are at certain specific frequencies of light. And then the red is our model fit to it. So we can generate a computer model of how SO2 behaves in the atmosphere of Io, and we can start to match it with the data. And so you can see that it matches the data pretty well. We have a pretty good handle of what's happening within the Io's atmosphere.
And this is the kind of thing astronomers live for, folks. They love that when the red line and the blue and the black line come together. That really makes them happy.
Yeah, that's right. When it matches. So a question. So the light in the black line is it mostly reflected light?
This is at a wavelength in the mid-infrared. So this is all heat that's being pumped out of Io.
Heat. Okay.
Yeah. So it's thermal radiation from Io.
So there's no reflected light from this, not much from the sun.
Correct.
Okay.
Yeah, this is at a wavelength called 20 microns.
Yeah.
All the way out in the infrared. So it's pretty cool.
That's right. So this is what you do.
It says 18.9. I see that now.
Yeah.
Yes.
That's right. So in every performance review of every astronomer every year, they want to be able to say to their boss, "Hey, my red lines match my and they
models are good
for another year." So that's really cool. All right. Well, let me get to some of the comments here that are on the website. Therion is asking, "Are there any theories why Io lacks water? I mean, it could be active core covered with ocean and icy crust like other Galilean moons. So why does Io not have this ocean as well? Is it so active? Has it already boiled away?" Good point. Good point, because Europa is right next door.
Right. Well, we think it's the second point you made. We think that at some point in the past, Io had water, but because of this heating process and a lot of the hydrogen species like water and pure hydrogen have just literally evaporated from Io's interior. And so at some point in the past, there probably was water coming out of these volcanoes, but now all that water's been driven off. And so all you're left with is the heavier elements like sulfur dioxide.
So they just couldn't escape. It couldn't go away.
it escaped away and couldn't be retained. So yeah, it just evaporated away.
Good question.
Can I ask a question of you? What's the temperature of these lava lakes?
Oh yeah, that's a really good question. So the temperature of the lava is the coolest is something on the order of 300 kelvins. So 500 degrees, Fahrenheit, Celsius, depending on what you want to use. The highest we think we've probably measured is something like 1,200 kelvins.
Kelvin or Celsius?
Kelvins.
Well, then 300 is kind of room temperature, right?
Yeah. So you have fairly cool. As lava spreads out onto the surface, it's radiating to space and starts cooling off. But the highest temperature of the actual eruptions we think have about more than 1,000 degrees Kelvin. So
yeah, okay,
pretty warm.
So that would also the water it would turn into a gas and then be easily blown off the weak gravity of Io.
Yep, for sure.
Okay, well, let me go to George Caldwell. Welcome back, George. It's good to see you again. For any moon to be geologically active, would it have to rely on forces brought on by its parent planet in all cases, since moons cannot support magnetospheres and thus active cores? Or if a moon is big enough for any other reason, could it be geologically active on its own?
Yeah, that's a really good question. We think that you can have a certain case where if you have a big enough moon, the heat, the radiogenic heating, all the radioactive elements that's still giving off heat from the formation of that moon, that should still be in there. So if it's big enough, you can actually generate geological activity by itself. So,
also, it's probably if it's young enough, too.
Yeah.
Because it'll be warmer when it was young and still collapsing or still forming.
Exactly.
Okay, cool. All right, well, Rainbow Panda's got a good question. Are there any concepts under consideration for Io landers? Anytime we're going to land there anytime soon? Juno, I know, is there now, but I don't think there's much on the drawing board. Is there to get us to Jupiter after that?
Actually, no, there isn't. So there's Juno around Jupiter. The Europeans are flying a mission called JUICE, which is going to look at Callisto and Ganymede. And they're going to fly it within the next 10, 15 years or so. But nothing.
When the heck is Europa going to get some attention?
And the Europa is actually, NASA is actually has already funded, starting to fund a flagship mission to Europa. So that's already on the drawing boards, and it probably will definitely fly. Io is the odd one out, unfortunately, out of those big 4 satellites. So no orbiters, no landers. We'll just have to do with big telescopes on the ground, unfortunately.
Well,
yeah, I mean, with the chance for liquid water below the ice on Europa, NASA would love to land there. So any lander in the Jupiter system, it's going to go to Europa.
True. One has to have priorities, doesn't it? Okay. All right. Rainbow Panda is also asking, what would be really cool would be building massive geothermal plants all over Io and beaming the power back to Earth, the Moon, Mars, and future space stations via laser.
I like it. I have no complaints. I have no complaints.
Sounds like an energy opportunity for Elon Musk, or even you, ain't Rainbow Panda, if you want to do that.
Right.
Larry Beckham, is the present screen cap available online? It's too small and fuzzy in the video feed. Oh, good point. Okay. Do you guys, let me ask my guests, do you guys have a problem with me putting this up somewhere where people can get it and look at it after the fact, downloading these images, these visuals?
Sounds good.
Yeah, right, no problem.
I'll put them up on my site, and then I'll put a link in the description box where you can download them yourself there. I just wanted to ask before I made that possible. Yeah, because sometimes the streaming quality isn't great, and some of those letters, especially in the schematic, was pretty bad. So
the schematic, I put the astronomer's shorthand for the reference. I think. Tony, let me send you a more detailed way that people could grab the paper.
Oh, even better.
Actually,
okay, good.
That came from.
Yeah, because I know you guys assembled these for the Hangout. So, okay, cool. Yeah, if there's a better source somewhere, I'll put that up instead.
Okay.
So here's a good question from Roldy. I love this question. Does Earth's aurora, you guys may not know this because you study Jupiter and stars, but does Earth's aurora have footprints of our moon? That's a good question.
It doesn't. I don't think it does, mainly because Jupiter's magnetic field is so strong, and there's a lot of free electrons hanging around Jupiter, which helps to form these footprints. I don't think that same process happens on the Earth-Moon system.
Also with the volcanoes, for example, on Io, there are a lot of particles that are leaving that moon, whereas there are not many of that particles leaving our moon in comparison. So there are a lot of particles that are going to stream down the magnetic field lines that are connected to Io.
Okay. Well, it is wish list time, and Chris DM is. I'm going to put this one on UConn. He's asking if you could send a lander to Io, what experiments would you want on it?
Oh, that's a good question. Everything. You know, as a scientist, you want everything on there.
But you only have $100 million, so
that's not enough. What do I want? Well, you know, so something that's really interesting is the idea of delving into a lava. You know, we're developing technologies that can handle the high temperatures and the pressures in these magma chambers. And it'll be so interesting to put a little, you know, robot down into these lava tubes that are active and flowing. So I'd love to go inside a lava cave.
Are you kidding? That'd be awesome.
That'd be
Those
awesome.
robots going in lava tubes.
Yeah.
I love that.
Absolutely.
That would be killer.
That'd be nice.
Okay.
We need to have a spacecraft that has a bunch of little rovers, and it goes from one moon to the next, and just drops off lots of little rovers. And
yeah, but you know who's going to have a problem with that? The planetary contamination people. They're going to be like, no, you can't take what was on one.
No, I don't mean they go one place and go to the next. The satellite carries 4 rovers.
Oh, and drops them
goes to each of the Galilean satellites. Each one gets one.
Okay.
It runs around and it digs around and it explores. Yeah.
Yeah. So, yeah, and Larry Beckham is commenting, and I think I agree with this, but you guys can comment. The space around Io would have a lot of radiation to fry a spacecraft. Talk about that briefly. Comment. Is it under a lot of bombardment with radiation from Jupiter?
It is, and actually, you know, Matt might know more about it. I think, Matt, are you associated with the Juno mission? But I know that Juno, you know, has a finite lifetime because of the radiation.
That's right. It's got heavy shielding on it too to protect.
That's right, and so it makes if you look at the Galileo mission that NASA sent to Io and the Jupiter system back in the early 2000s, they flew by Io only just a bunch of times because it was getting fried so badly. And so it's a real challenge to design, you know, spaceships that can handle that dose of radiation.
Yeah, that would be. Well, do you have any comment to add to that? Is it special considerations for radiation there?
I would say it's just what Con was saying, and I'm not involved with Juno. That's Tommy Greathouse, one of a mutual colleague who helps run TechSeas a lot of the time in order to study Jupiter and the weather on Jupiter.
Yeah, and you know, actually, I don't know if it's true for Juno, but a lot of the missions that go to Jupiter are designed to go to Jupiter have these shield boxes. You put all the electronics, all the sensitive stuff in this, you know, vault made from lead. You know, so that's the only thing that can keep out this huge dose of electrons and high energy particles, and that's really heavy. So that makes going to Jupiter really challenging.
All right. Well, we are going to. I'm going to cut it off there. We are out of time, folks. I want to thank all of you for commenting on the website. I hope you guys are liking the chat feature. I know I am, because it's a lot easier for me to keep track of the conversation there, and it doesn't seem to be filled with a lot of the noise that goes on YouTube. So I really want to thank you guys for joining me on deepastronomy.com/live, and I hope you're enjoying these Astro Coffees, because I'm learning a lot in every single one. And this is like I said at the top, this is your glimpse into what real astronomers do all the time. They get together over coffee, they have cookies, whatever they want. They just spend some time and chatting. So I hope you enjoyed your coffee. I hope you got something out of today's hangout. I want to thank my guests, Dr. Constantine Tsang from the Southwest Research Institute, also Dr. Matt Richter from UC Davis. Thank you both for taking time out to join us. You guys got any future observations planned on Gemini North, or is this it? Have we settled the case?
Well, we're writing proposals. They're due next week. We're hoping to go back in February, but it's not a good I/O time. Con and I were talking about.
Okay. All right. So that's right. You got to get the
next time.
Right. Yeah. All right. Well, Carol, we got another one behind us. I want to thank you for setting this up. This has been awesome. Next week we have it lined up. What do we have next week?
We have to look. That
and we're talking. No, I have it right here. I'm just looking it up.
You have the calendar.
We have more than 100 exoplanets covered with the Keck space, or confirmed with the Keck Space Telescope, and we're going to be talking with some of the researchers.
No, Keck is not a space telescope.
K2. Space telescope? I'm sorry. Keck is not a space telescope.
No,
right.
It's a ground-based telescope.
What did I say? Keck Space Telescope?
Yes.
So I'm busy reading and talking. I need to be more careful. So we'll be talking with people.
It's really not that far from the 8 meters. So,
no, that's right. It's behind the stone's throw. That's right. It's all right there. All right. So that is going to be our next week in our Astro Coffee. I want to thank again our guests for watching. I want to thank all of you for talking or for showing up and interacting. This has been a lot of fun. And we will see you next week. And as always, hey, keep looking up.
Bye-bye.
Bye. Right, thanks.